Action.
Okay, so for those of you who missed the Hetero Carp 2019, so I gave a talk yesterday regarding the multifractality of the superconducting state in a single layer of niobium diselenide, which is a a truly two-dimensional superconductor that was discovered a few years ago. Okay, so what is multifractality and why the superconducting state of this material is multifractal in nature? So the concept of multifractality comes originally from the Anderson transition, which, so basically if you think of an electron, non-interacting electron in a disorder potential, which basically describes disorder material or a material with some sort of disorder. So if you treat that problem classically, no matter how much disorder there is in the system, the electron will be able to diffuse along the crystal lattice. But if you treat that using quantum mechanics, Anderson realized that beyond a certain amount of disorder, the electron gets trapped in the lattice, and therefore the material becomes insulating. That's what it's called, the localization Anderson transition. And so when you add disorder in a material, basically you start from a metallic wave function where the electrons are be able to diffuse throughout the material. When you add disorder, basically everything evolves towards the localization of the electrons. But there is a point which is called the critical point at which the wave functions that describe the system are neither metallic nor localized. It's something in between, which is called the multifractal regime. And this is something that we wanted to study in single layer niobium diselenide. And the reason is because this is an effect that is boosted in 2 dimensions. So in 3 dimensions, there is always just a narrow window where you can see this effect, whereas in 2 dimensions, this can be seen even in the presence of minute amount of disorder. So we basically, what we did was to grow single layers of niobium diselenide on graphene by molecular beam epitaxy. And then basically we characterized the electronic structure by low temperature scanning tunneling microscopy and spectroscopy. What we did was to map the superconducting gap in clean regions of the material, okay? And we map the width. The width in a superconducting gap is basically proportional to the superconducting order parameter. So we basically were able to map this with atomic resolution. So what we found is that the superconducting order parameter in this material follows some fluctuation, is not constant as it should be expected if it was a clean material. Instead, we were able to observe fluctuations with a very characteristic wavelength of 7 angstroms, which we found coincident with the quasi-particle interference wavelength that happens in this material. So we realized a statistical analysis of these widths, and we found 2 things. First is that the distribution of values of the superconducting order parameter, or the width, is what we exactly measured, follows a log normal distribution. It's not a Gaussian distribution, it's a log normal distribution, which is the first fingerprint of a multifractal entity. The second fingerprint of multifractality was the 2-point correlation function that we calculated in our experimental windows, and we found that this 2-point correlation function was showing not an exponential decay, but a power law decay with a very characteristic exponent, which was coincident with the log normal distribution. And basically, these 2 fingerprints are telling us that the wave functions associated with the superconducting state in this material in 2 dimensions are basically multifractal. So the importance of this work is that basically we were able to demonstrate this multifractal state in a two-dimensional superconductor. But in principle, if this is true, this should be applicable to other two-dimensional superconductors, such as, for example, iron selenide or most of the known two-dimensional superconductors known to date, which basically show large spin-orbit coupling. And that's pretty much it. Thank you very much. I don't know.